G'day, Lance from Motive Power, back again to talk a little more about professional off-highway vehicle design. Today we're talking about engines, primarily diesels, and how to best incorporate them in your vehicle design. As usual, everything I say is not advice, it is merely guidance, suggestions for your further research. That said, let's start with some terminology. We're talking about engines today, thermodynamic devices. They are not motors. Every time a mechanic says, I'm going to tune your motor, you need to find a new mechanic, because he doesn't know the thing he's working on is an engine, not a motor. In a conventional car, the thing under the bonnet or the hood is an engine, it's not a motor. The only motors involved are windscreen wiper motors, windscreen washer motors, maybe electric window motors. So we're going to try and use the right terminology. Motors are not thermodynamic devices. Engines are. Diesel engines burn fuel, they create heat, which is turned into work. Thermodynamics at action. Steam locomotives are steam engines. They may have steam motors on board, but the actual creation, the actual driving force for that locomotive overall is a steam engine. So let's call the things by the right name, engines. Now, the first thing everybody wants to know about an engine is what's its power. We usually say, how much horsepower? Okay, I'm in Australia, we're metric. I should say how many kilowatts. But for the purpose of this discussion, I'm going to use horsepower. When you deal globally, as I've said before, you have to be very careful of the terminology. A horsepower is 746 watts. A kilowatt is 1,000 watts. If you're talking to a Japanese customer, however, there's a fair chance he's using a metric horsepower, 750 watts. Not a big difference, but it can add up with big size engines, big power engines. So when you're talking about power, as usual, get the terminology right. If need be, educate your client. Trust what he says, but verify that he understands what he's saying. Now, there's terminology that engine companies use. I think they're all the same, and it's all nuts. I've built a lot of vehicles in my working life, designed a lot, and every one of them has had an industrial engine in it. I've argued long and hard with engine company reps to say it's a vehicle. It's got 4 wheels, a steering wheel, an engine, transmission. It's an automobile. But no, it doesn't get an automotive engine. No. It has to be an industrial engine. That terminology will plague you, because industrial engines are sold by engine companies with a whole different suite of options. You'll probably find you have a different fuel pump, different manifold options, different turbocharger options. If you're making a genset, it's probably ideal, but it's very tricky when you're making a vehicle. When an engine company rep says to you it's an industrial engine, get suspicious. Trust but verify again. Find out exactly what he's offering and just don't accept it. Push hard for the automotive versions. You may find that you've got to buy an industrial engine and retrofit it with automotive componentry. So far in this series, we've talked about a number of other parts of the vehicle. In reality, everything needs to be done in parallel, but the sequence we've followed is probably a good guide for the sequence that you would need to go through. We're now at the point where we need to really nail down what engine is in there, what sort of power, and begin to talk about all the ancillaries. So the first thing you need to know is, how much power do I need? When that power is used to propel a vehicle, that can be a relatively straightforward answer. Tractive effort times speed gives you power at the wheels. Sometimes, however, the power you fit is also going to be used for auxiliary functions. It may be that there's a truck or a concrete mixer with an engine that's fitted to drive that truck, but that engine is also used periodically to drive the mixer, to drive a drill rig, or a range of other functions. So perhaps you need to establish the power for various load cases, but you need to work it out. We're going to focus initially on the power to drive the vehicle about. So you're going to need to know the weights, the resistances, the air resistance, the grades, and so forth. And somewhere in there, you'll be able to work out how much power is required at the wheels. Now, getting that power to the wheels involves things called efficiencies. And they're always less than you like. You're always going to lose significant amounts of power just in the drivetrain. More and more as the vehicle becomes more complex. Typically, I will assume 95% efficiency for a gear set. And that's a fairly nominal number. You might argue that it's a high quality gear set that should be 97%, but generally 95%. But the problem is, if you have a torque converter, transmission, a drop box, a differential, a planetary gear set, so forth, you can get, say, 6 times 95%. It's a compounding situation. So although an individual component in that drivetrain might be 95% efficient, the reality is that overall, if there's 6 of them, you're going to have 74% efficiency. So if you've worked out that you need a whole 250 horsepower at the wheels, then that means you need 340 horsepower at a flywheel. Big jump, big change in engine sizes. But wait, there's more. Your engine probably is driving hydraulic pumps, air compressors, fans, and lots of other ancillaries. Fans in particular are a big draw. Easily 50 horsepower on a 450 horsepower engine. So overall, to get 250 horsepower at the wheels, you're going to need something around 420 horsepower at the flywheel, well, not at the flywheel, gross from that engine. Now, sure, you can get away with less, but at some point you're going to get caught. It won't perform to your specified performance. If you oversize, yeah, you can get away with that. But it's also possible that you'll end up with glazed bores and oil pouring out the exhaust pipe because you've used too large an engine on too small a job. And of course, if you upsize the engine, everything else goes up too. Torque converters, transmissions, drop boxes, drive shafts, and so forth. So be very careful not to oversize. Okay, you know what power you want to use now. So we've got to select an engine to do it. And that's done using specification sheets from engines. You'll probably find your customer, or indeed you yourself, may have a brand of engine preferred, Caterpillar, Detroit, etc. But I'm going to use some Cummins information as an example. So this is first page of a multi-page data sheet from Cummins. It happens to be a Dongfeng engine for a 5.9, 6B 5.9. Most people will look straight to these curves. If you're interested in horsepower, that's where you're going to be looking at a power curve. Sometimes people will look at a torque curve and be very keen on what the peak torque is. I'm going to be controversial and say that peak torque doesn't matter. The role of the gearbox and the drivetrain is to create torque. There are two reasons for worrying about torque. One is that it makes the vehicle more drivable if it is at lower RPM. And that's typically the reason people like V8s. Apart from the raw power, it tends to be low down and they can get off the line easier. The other reason that torque is important and the speed at which it happens is important is in this third curve down here. This is fuel consumption. So generally, peak torque coincides with the minimum fuel consumption, grams per kilowatt hour. So the further down the hill that comes, the better, because that means that you can get a highly efficient vehicle running down the highway. And you probably realise that even in your family car now, you've got 6 speeds or more, and if you're going down the freeway, you're at very low RPM. The reason for that is efficiencies. The lower the speed of the engine, the less losses within the engine. Now, I said most people will go straight to the curves, and they will overlook the fine print. And in anything, the fine print is important. Engine in testing with fuel system, well, that's good because it wouldn't have run without it. Water pump, that's probably good. Oil pump's definitely good. And no air compressors, alternators, fan or optional items. So this power curve does not represent the real engine, because in the vast majority of cases, it's going to have an air compressor, alternator and fan at the very least. We've already said that fans are a big power draw. So you need to take these curves, let's say the power curve, and superimpose on it, perhaps underneath it, the power draw from the ancillaries. And that'll tell you perhaps that this engine isn't big enough. Always read the fine print. Now, in this particular case, it's pretty good. It actually says inlet manifold and exhaust back pressure. Doesn't say what temperature was, but it's probably 20, 25, somewhere around there. They're also important characteristics. So let's assume we've picked an engine. If we go down this data sheet, first thing I like to do is select the components for the air intake. Because without the air intake, it's not going to run. And here's some key data. Maximum intake restriction, clean element, dirty element. This is not the total resistance of the air intake. You still need to allow for pipe work and perhaps a whole heap of other things being air shutoffs and extended pipes. But it starts to give you a pretty good idea of what you need to size your air intake. Cummins also have this thing about dirt holding capacity. So it's suggesting a heavy duty air filter with 53 grams per litre per second of dirt holding. If I remember correctly, that's because they have a minimum in service life of the air filter. I presume that's to try and stop people using air filters for extended periods. So now you've got some basic characteristics for the air filter that you require. For me, I usually design a system that's got a resistance 3 times that of the air filter. That's typically for mining because there's a lot of other things that get inserted into the intake system, but I can come up with a number. I then have to figure out the packaging. Now for mining, it would be a metal housing, not a boxy little plastic box. Something robust that's going to survive the duty. And we're going to use a Fleet Guard example here. Here's a chart for metal air filters. Now metal relates to the housing, not the element. And there's a range here of flow rates, and if I just move down a little bit, in CFM. And you can start to see how you might select one. Now this gives you the option of red with no safety element and black with safety element. I would suggest it's a very brave or foolish man that designed something without a safety element. So we're going to look at the black. So if we know we need 900 CFM, we're going to be somewhere up in this range. You want to be right at the top end, or do you want to have something a little bit in reserve? So that's starting to give the selection of filters that you could use. So we'll just flip down and find the AH19074. Now we've tentatively selected a model, we can look at some of the characteristics. The lengths, generally the filters are too damn big to fit. And that's why this step of selecting filters is very crucial. You'll see dirt holding here and dimensions, specifications, and if we go down, we get more information, and even in this catalogue a suggestion of accessories like hoods and elbows and so forth. And there's the actual performance for this filter. All of this information is readily available and should be used, should be investigated, and make sure you've got the right product. The same sort of review is possible for the exhaust system. And again, we'll use some Cummins data. So back here on our data sheet, right next to the air intake system is the exhaust system. Maximum back pressure, exhaust pipe, etc. So you straight away know what exhaust pipe you should be using, and you can start to work out what muffler, exhaust conditioner, spark arrestor, etc. that you require. So this again is core data that's readily available. Up to here. Right. But of course in exhaust systems that isn't the end of it. You're likely these days to have a DOC or a DPF to either oxygenate or otherwise treat the exhaust. DPFs come in 2 types, wall flow or flow through. advantages, disadvantages for both. They're designed to handle particulates. DOCs are generally designed to oxygenate the exhaust to allow other combustion processes to happen, and they often form the first phase of a DPF. These things are expensive, they're generally sensitive, they don't like an engine idling for a long time and then put into heavy duty service. You'll probably melt something, an expensive something. If you're running ceramic wall flow DPFs, you're probably going to have scheduled burn-off times to get rid of the particulates that are trapped inside. Again, another complex subject, not going to be covered in detail today. Many mining applications also have exhaust gas coolers. They can be of various types, but typically some sort of heat exchanger with special tubes that the gas runs through and cooled by water, typically from the engine water jacket. Some flow is stolen from the engine block and passed down through the gas cooler. So again, that's more resistance that you've got to design for in the exhaust system. And somewhere in there, if you're on highway, you might have an EGR, exhaust gas recirculation. Probably less manufacturers using EGR now because of reliability issues, but it's still out there in the market. And if you're in coal mining, you're going to have flame traps of various types, maybe water-based, maybe mechanically based. But it all adds to the back pressure that you have to design for. Do the numbers, end up with a reliable system. So hopefully you now know what engine, you know what power, you know how to let it breathe and how to do the exhaust. How do I connect it to anything? Well, it's usually through the flywheel. Not entirely, but usually. And that brings in a whole other subject. So we're going to look at flywheel connections now. This is just a diagram of a flywheel, engine flywheel. Crankshaft would come off here inside a flywheel housing. Now we're very lucky. There are SAE standards for flywheels, and there are SAE standards for flywheel housings. What there isn't is a standard that relates the flywheel to the housing. So you'll probably nominate the flywheel housing, certainly, to your engine supplier, and then you'll say what flywheels are available. You need basically to get all of these dimensions and give them to your transmission supplier so he can make sure that he can adapt. You may find you need an adapter because you can't go from flywheel X to housing A, and there needs to be a conversion in the middle of it. It's a crazy situation, but that's the reality of it. Now, some sort of transmission will plug in here. It will hang off the flywheel housing and connect to the flywheel. Whether it's a generator or automatic transmission, the same criteria apply. You have to match housing and the flywheel. But of course, it's never that simple. Even if you get a good match. So let's look at the left-hand diagram here. This would be typical of a transmission. It says torque converter. If this was a generator, it wouldn't be a torque converter, but it would still likely have a flex plate. So here we have a flywheel, and a crankshaft, and a torque converter, and a flex plate. The flex plate being bolted to the flywheel, and then also bolted to the torque converter. It's there to allow for minor misalignments and just take out some shock loads. Now, the problem is, not only have you got to make sure the flywheel housing of the engine matches the flywheel housing of the transmission, and that the flywheel of the engine can be connected to the input of the gearbox, you actually need to be able to do up these screws. Now, these ones can be done up readily without the transmission attached. When that transmission is bolted up, even on this diagram, there's no access way to get that screw in. Now, I have had engines and transmissions from the same manufacturer involving the same manufacturer's engineering team where the two bolted up perfectly. But no one left a hole down here so you could get a spanner in to get that screw tight. This sort of silliness does happen. It's a regular part of trying to match engines to transmissions. You need to be aware of it, and you need to be on top of it right from the start. So we're now going to talk about cooling the engine. And once again, we'll go back to that Cummins data sheet. We go further down the data sheet, there's the cooling. How much coolant, flow resistance, usually you get pressure and so forth. What your thermostat is doing, pressures, temperatures, flow rates, etc., etc., etc. Now, this is really good data. It's not the full amount. It doesn't tell you how important drawdown is, for example, but it's the start of what you need to determine how the engine is going to be cooled, or what the engine needs to be cooled. And if we look here, it also tells you some interesting things. The normal engine operating temperature at maximum is 100 C, but your shutdown sensors are supposed to operate at 101.6. So what that tells me is this engine does not like getting hot, and that how much the system is pressurized, you're definitely going to need a 50 kPa cap or more. You may need to pressurize it more so you can get more cooling out of this very small safety band. In reality, there's never enough room for cooling. Cooling is quite big. You've had enough trouble fitting the engine in. Now you've got to get this damn big radiator in. And worse than that, the hydraulics needs a cooler. The transmission needs a cooler. Maybe there's an aftercooler involved as well, an air-to-air aftercooler, which I hate because of piping. I'll go to a jacket water aftercooler any day. The typical unprofessional approach is just to stack those coolers up in front of the radiator. And you can get away with that to a certain extent. But what you're doing is then, assuming it's a sucker fan and you're stacking in front of the radiator, you're then giving the engine radiator higher temperatures and less flow than it needs. The air coming to it is already preheated by all the other coolers in front of it, and you're not getting as much air through because the resistance that the fan sees stops that flow being what it should be. You need to think very carefully about where those other coolers go. If you can, stick them somewhere else with a little electric fan. That's not always possible. For example, underground coal mines, electric fans are not a real possibility. Perhaps don't stack the coolers. Put one above the other against the radiator so that you're minimizing the damage. Or put them on the hot side of the radiator. Typically what happens is that engine has more temperature sensitivity than the transmission. So let the transmission get hotter. It's designed to, it'll work better that way, but keep the engine cool. Think very carefully about the overall cooling package, and don't just think about it as an engine cooling package, because you have to consider it as a vehicle cooling package. Even if you're the engine supplier, some other turkey's going to want to shove lots of other things in front of your radiator, whether you tell him not to or not. Now, a few quick words about fans. They can suck or they can blow. Both are fully acceptable. But how well they suck and how well they blow is dependent on which fans you've selected and how you've fitted them. Generally, if the vehicle has a prime direction of movement, put the radiator at front and suck. Typical car. If the vehicle is bi-direction, start to think about which is the most usual direction. If it's a loader, you might still put it at the back because you want the engine at the rear for counterweight purposes, but you might make it a blower fan, so you're not sucking all the dust into the engine compartment. If it's a locomotive and it operates in both directions, then put the radiator at the top or the sides. But when you do that, be very careful that if the two locomotives are operated together, double-headed, that there isn't a pathway for recirculation between the two, particularly in tunnels. That'll result in the trailing locomotive overheat substantially because it's seeing all the hot air left behind by the leading locomotive. So generally speaking, it's not done this way, but generally speaking, if you can, get the radiators on the side so they're at least different sides when the locomotives are double-headed. Now, the fan position in the cowling is also crucial and generally not appreciated. The way I think about it is the fan has to stick out enough into the incoming airflow to be able to grab hold of it and drag it through. Now, in practice, if it's a sucker fan, half to 2/3 of that fan width needs to be in the cowling, actually in there, getting the air and blowing it out the back. If it's a blower fan, half to 2/3 of the fan needs to be outside of the cowling so it can grab it and push it in. And that measurement, if you've got long, perhaps twisted and tapered blades, needs to be at the blade tip. It can result, and I've seen it happen, a fan in the wrong position, something that looked right to the eye, but not optimal, 1/10 the airflow. And that's a big impact on cooling. When you're thinking about cooling systems, don't think about them in your design office or even in the factory. Think about where it's going to be used and what are the real conditions that it will be used under. From a cooling perspective, anything down to minus 25 C is fairly straightforward. And anything up to about 45 degrees C is okay too. Above that, you start to get quite large and have to think very carefully about what you're doing. A lot of people will quote weather station data. Yes, it was only 40 degrees here on this day, and that's the evidence of our design basis. That can be very misleading. Weather stations use thermometers based in Stevenson screens. That's a white louvered box a certain distance off the ground the thermometer is in the shade and it has an airflow through it. I've no doubt the readings are very accurate inside that ventilated, louvered, shaded box a certain distance off the ground. However, if you're in the Middle East, Northern Australia or other hot environments where the ground surface is 70 to 75 degrees and there's a heck of a lot of heat reflected off that surface, whatever is in the Stevenson screen is not going to apply to where your vehicle is actually being used. You need to think very carefully. For example, low-mounted radiators in the Middle East are probably going to see 60 to 65 degrees. Even if the weather station says, no, it's only 45. Because out there on the sand, it's a very hot environment. Even working in underground coal mines, the design requirements are 40 degrees C. To be honest, if I'm in a coal mine at 40 degrees C, I reckon it's on fire and I'm getting out. But that's the design criteria we have to work to here. And that's great. It's easy. It's moderately easy to get a radiator that size. But what if it's in Northern Australia and it has to come out of the mine and drive across, 50 degree surface to get to the workshop? And what if it is 50 degrees in the workshop? Okay, the vehicle might not be working, but it's still going to see that temperature. You need to have that in mind. Now, at some point, you may end up with an engine on a dyno. And, we've looked at some dyno curves earlier, some performance curves, and they will typically be done at 20 to 25 C. If you want the same power at 50 degrees, 40 degrees, you're not going to get it. Even if you're dyno testing, I've seen dyno cells that have gone over 50 degrees C because they're not well ventilated or not sufficiently well ventilated. Again, that'll screw the numbers that you're getting and you'll need to make allowance for it. If you've got an engine under test developing 100 horsepower and it's 55 degrees in that test cell, it's probably going to get 110 horsepower if it was 40 degrees, and maybe even more if it's 25 degrees. So your horsepower is going to vary as well. Humidity also has a part to play, but to a lesser extent. So make sure your test results and your performance curves that you're working to relate to real world conditions. Of course, before we get any sort of dyno test, we need to start the engine. Generally with larger engines, it's not electric. If it's electric, you need big batteries. You need to make sure you meet the CCA requirements for that engine. That's the cold cranking amps. You need batteries that will produce that at the minimum temperature. A lot of engines, particularly electronic engines, need to reach a minimum cranking speed before the computer turns on. So you need to be sure you can meet that CCA. And that's the CCA figure for the base engine. As we saw earlier, that's probably without the compressor and the fan, and oil pumps and all the ancillaries. So you need to be able to do better than that. For big engines, the size of the batteries and the size of the starter motor or motors becomes prohibitive, and you tend to go pneumatic. Most of the vehicles I've designed have probably been pneumatic starting. Now, air's simple. It's all around us. You pump it up, you put it in the tank. You want to use it for a starter, get a damn good air starter, like one from KH. And, well, you need big lines, and a big tank, as big as you can physically fit, because you're probably only going to get 2 or 3 starts. If your engine doesn't start first, second, or maybe third time, you're out of air, and you'll need a provision to replenish it. And that brings in other factors. Most mining vehicles with air starts have a port quick connect, and then there's the problem of, well, how do we know the hose has been disconnected before you drive off? So they have to have a sensor, and it complicates the whole deal. Air start is effectively quite easy, but it's damn bulky. I mentioned earlier engine companies talking about automotive or industrial. One of the areas that severely impacts is throttle control. And the throttle is linked to the governor. So I'm going to simplify some of the terminology. I'm going to say there's just 2 types of governors: an automotive governor and a variable speed governor. Automotive, the way it works, you put your foot on the throttle and you put a certain amount of fuel into the engine. And the engine goes to whatever speed that amount of fuel will permit it to go to under that load, just like a car. And the governor probably prevents overspeed. So you can push as hard as you like on the throttle and you won't exceed 2500 RPM or whatever. The alternative that's usually fitted to industrial engines is a variable speed governor. So the throttle position sets the speed you are asking for. In round numbers, you go halfway down on the throttle, you'll get a 50% increase in speed, providing the engine can provide the power to achieve that speed increase. So the throttle relates to engine speed. The throttle links to the governor, which controls the engine speed. You can use that sort of arrangement on vehicles. I've used them on locomotives. But it gets very confusing trying to explain to operators that their throttle is not like their car. Again, this is a situation where you need to work very closely with your engine supplier to try and get the right governor for your application. So now I'm going to move slightly away from the technical, maybe a little bit to the politics or the reality of the situation. Lots of engine companies sell engines, and there's a range of them. You can start with JCB right through to Detroit Diesel. Generally your client will have a preference, or perhaps you do. It needs to be managed to see whether that suits the application, but generally you'll go along with what the client wants. Theoretically, there are lots and lots of options available. There is effectively no such thing as a standard engine. Maybe not even the crankshaft or block. The reality, though, is it gets very difficult to have a bespoke engine, because the engine companies by default want to spit out standard engines that they are building for other clients. If you're a low build customer, low quantity customer, they're not going to do a whole lot to make sure that what you've ordered is what you get. I've had multiple examples of engines arriving, ordered to a spec, and they didn't meet the spec. Different flywheels, housings, engine mounts, front covers, fan drives. It's quite common. And then you get back with your rep and say, I'm not paying because it's not what I ordered, and blah, 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 and it gets very confusing. If you can find a standard spec that they're building for somebody else that's reasonably close to what you want, and get one of those and
perhaps get your local distributor to rework it to your specific requirement. Be aware though, it doesn't mean because you've ordered something to a spec doesn't mean that's what you're going to get. And then we get to emissions. Nightmare. Understand and agree with the approach of everybody. We want the earth to be a better place. For a vehicle builder, it's just a traumatic space to be in. And it depends upon the part of the world that you're in. The local regs, sometimes being an export order isn't easy. People think that if you're using an engine that isn't a low emission engine, that you're some sort of shonky operator. But the reality is, it's really only Europe and the US that have tight emission limits, and they have the fuel qualities to make it possible to use engines with those tight emission levels. I've seen the outcome of American-made drill rigs with, I think, Tier 4 engines going to Eritrea. They lasted a few weeks. The entire fuel systems had to be changed at a cost greater than the engine cost itself, because the fuel available in Eritrea was not of the quality that was suitable for a low emission engine. This is a big problem. Now in Australia, from memory, sulphur, which is the key indicator of a low emission fuel, is 5 parts per million. But I've seen it specified low emission diesel fuel at 500 parts per million in parts of Asia. So be very sure of what fuel is going to be used in the engine in service, and select an engine to be right for that sort of fuel, because that's something you're not going to change. You know, I've had to deal with situations in China where the fuel is known as number 10 diesel because it comes out of the number 10 diesel factory. Get what data you can, get the data sheets, get the name of the fuel, get the supplier, get on the internet, trust but verify, find out what that fuel is, and make sure that the engine you are buying to put in your vehicle is suitable for that fuel. Now, I understand in the US that's a problem at the present moment. You need some sort of government approval to have an engine that is not low emission, even if you're building the vehicle for export. So there's lots of considerations around emissions. Generally off-highway worldwide, nobody bothers about it. You know, in places like oil rigs, nobody cares. They're in international waters, so who knows what rules apply. But if you're designing for an export application, and even for a local one, make damn sure you've got an engine that matches the fuel that will be used. Now, we've spoken a little bit about the data sheets from engine suppliers. That's actually only the tip of the iceberg. Every engine manufacturer will have a huge array of guidance available for that model of engine. How to mount it, how to cool it, how to control it, how to protect it. For Cummins, they're called AEBs, Application Engineering Bulletins. Every other company has got a variety of descriptions, but they're all there. When I used to use a lot of Detroit diesels, the manual was that thick, and I could look up everything in it about power takeoffs and all the rest of it. Make sure you've got all the AEBs or equivalent, you've read them all, you comply with them all. This is about warranty, and in reality it's about less embarrassment of the engine braking. You may find that there's a local application engineer for that engine company. They can be a great resource and you should use them. Ask their advice, get them involved, because if you want to go the whole hog and get fully warranted, you're going to have some sort of installation review and sign off, particularly if you're going to be buying engines in volume. It's all about that engine company covering their tail in regard to warranty, just as you should be doing. And of course, there's the usual curse of how am I going to fit all this stuff in the small space I've been given. You know, I spent a lot of my life in working in low profile vehicles for aviation and underground mining. They're always about nose high, another 6 inches. It's a bit like my height, another 6 inches would make a big difference, but you can't get it. So you have to work hard at getting the most out of what you've got. Probably good advice for life. Packaging is an issue. We're talking about engines. The engine companies like making inline 6-cylinder engines because that's what they make for high volume trucks. If that fits your jewelry, great. Chances are it won't fit your aircraft towing tractor. Sure as hell won't fit an underground mining machine. So you get into V configurations, you get into twin engine configurations. Somehow you're going to have to be very smart and fit everything into the space you have. You will never have enough space. That's why I don't like air aftercoolers, because the pipework takes up too much space unneeded for other things. So packaging is important. Now, having crammed the thing into the hole that's available, you also have to think about how to service it. Am I going to get phone calls from the service department going, we can't get the oil filter off, we can't reach it, we can't get spark plugs out because the whirl well's in the way. My test is how easy is it to change a fan belt, and it often isn't easy at all, particularly on mining equipment where they're paranoid and everything's under a guard even though it's under a bonnet. So to get to the fan belt, the bonnet's up, the guards are disassembled, half the radiators out. I've seen it easier to pull a radiator out to change a fan belt than to do it any other way. These things need to be thought about at the design stage. You need to be thinking about it. Those AEBs from the engine company will give you things like clearances required to remove oil filters and dipsticks and so forth. You need to read them and apply them. So that's the outline of how to select engines. There's a lot more to it. We could have talked at length about air compressors and fuel pumps and alternators, shutdown systems and PDOs, but there's the core of it. You must take the time to read the supplier's technical info. It's there to help you. It might be a pain to start with, but it will avoid all the hard questions. I've sat in my office in Sydney, in Australia, and I've taken a phone call from Urumqi in China. That's about as far west in China as you can get. Vehicle will not go. What do we do? It's hard to do that thousands of miles away. Fortunately, it wasn't a vehicle problem. Someone had actually stolen the batteries. But you must understand, if you're in a global market, you don't want problems overseas. It's too damn expensive to fix. It's too damaging to your reputation, and it takes too much time away from other things. So read the data, learn what you need to, and apply that learning. Get the installation right. Engines are obviously critical to being used in your vehicle. If they don't work, the vehicle doesn't work. It's also can be a bit of bragging rights. My engine's bigger than your engine. That's cool. Clients like to know what they're getting, but it's got to work. So get all that right, do all that homework, cover all of those issues, and move on to the next stage of the design with a higher level of confidence.